Today we will continue with the alternating currents. During the last lecture, we have seen phasors and we have also seen reactances in AC circuits. We have also discussed resistor in an AC circuit. We have discussed inductor in an AC circuit, capacitor in an AC circuit, and LRC series circuit with an AC source. So we have discussed all these things. So during that lecture, we will see power in a resistor. We will also see transformers. We will also discuss resonance. So actually, if you understand the topic in the previous chapter, you can easily understand that part of the lecture. So let's continue with the power in a resistor. So here we have an AC circuit and we have just pure resistor, only resistor here in the circuit. So what is the power here? During the last lecture, the current is given with that relation. This is the current amplitude I and cosine omega t. So current changes as a function of time. So this was the current from the last lecture. So this is the current changing by time, okay? So we have also calculated the instantaneous voltage across that resistor in an AC circuit. This is current times R. Since current is written with that expression, so we have time varying voltage across that resistor. So this voltage is given by that function. So if you would like to write the power, instantaneous power, which is given by V times I, then just multiply them. So we will get V times I times cosine square omega t. So this is the instantaneous power for that circuit with pure resistor. And then we have power with black curve. This black curve shows us the power and it also changes as a function of time. So due to that relation, okay? So VI here is the amplitude of the power. So this is the power in a resistor. Then what about the average power? If you look at that curve, this black curve here showing the power as a function of the time, instantaneous power. So the average of that power is this one, half of it, okay? What do you see here? That the power is always positive. Instantaneous power is always positive, always on the positive side due to the cosine square omega t. From voltage, we will have cosine omega t. From the current, we will have cosine omega t. Then we will have cosine square omega t. So we are staying only at the positive side for the power. And if you take the average, average is given by that expression, 1/2 V times I. So average of cosine square omega t is 1/2. We have done it during the last lecture. So now we have average power, you see, half of it, 1/2 V times I, half of the power amplitude. So instead of writing VI half, we can write like this, V over square root of 2 times I over square root of 2. Okay, so if you multiply them, you will get the same result. So from the last lecture, we know that this gives us the VRMS, and this gives us the current RMS. RMS current, RMS voltage. We have discussed all the things during the last lecture, okay? So here we have VRMS. So instead of VRMS, we can write IRMS times R, resistance of the resistor. So take this VRMS, put it there. So finally, the average power can be written like this: I RMS square times R, or V RMS square over R, or with just that expression, V RMS times I RMS. This is the power in a resistor in an AC circuit. Do you have any question here? So then let me continue with the power in an inductor. Here we have just single inductor in an AC circuit. So these are the phasors for the current and voltage for the inductor, and there's a 90 degrees phase difference. This is the phase angle phi. We have discussed all these things during the last lecture. So in case of, let me remind you that in case of resistor, the phasor of the current and voltage phasor are in phase, okay? So phi angle is 0 in case of resistor. But in case of inductor and capacitor in an AC circuit, there's a 90 degrees phase angle. And in case of inductors, voltage phasor leads current phasor, but in case of capacitors, current phasor leads voltage phasor. We have discussed all these things. I will not go into detail today, but I will just keep these phasor diagrams here, also for the capacitor, for the next transparencies. So what we have here, we have voltage phasor leads current phasor with 90 degrees. So what about the power? Power here in an inductor, in an AC circuit. So look at the current. Current is given by I times cosine omega t. And the voltage across that inductor, which we have calculated during the last lecture, I times omega times L times cosine omega t plus 90 degrees phase angle in between. So I is the current amplitude, omega is the angular frequency, and L is the inductance of the inductor. This is the voltage across the inductor. So what we have here, this is the current. Current is changing as a function of time with that function, cosine omega t, okay? And this is the voltage. Voltage also changes as a function of time with that function. So what about the power? If you multiply current and voltage, we can calculate the power. So this black curve here is the power in the inductor. So what do you see here? That the power also changes as a function of time, and it is symmetric around the horizontal axis. Okay, this is the power. So it becomes positive, negative, positive, negative, positive. So what about the average power? Since it is symmetric around the horizontal axis, the average power is 0. Okay, average power is 0, but the instantaneous power is oscillating like this with that function, cosine omega t plus 90 degrees times cosine omega t. But the important thing here is that, look at this one. Current here in that region, current is positive, but voltage is negative. You see, positive, negative. Then here we have negative power, and here we have negative voltage, negative current, negative times negative, positive power. So the power is negative when V and I have opposite signs, like this one or like this one. And power is positive when they have the same signs, like this one or like this one. So this is the power in an inductor. But what about the average power? Don't forget this. The average power in an inductor is 0, okay, in AC circuit. So let's have a look. The power in a capacitor. So again, the current changes by time with that function I cosine omega t. So voltage across the capacitor in an AC circuit we have calculated during the last lecture. It is given by I over omega C times cosine omega t minus 90 degrees. So we know that the current phasor leads voltage phasor with 90 degrees. We have discussed this one. Okay. So then the power is given by VC times I. Okay. So how it looks. So this is the current given with that function, and this is the voltage across the capacitor changes as a function of time. So this is the voltage. Okay. And what about the power? Power is given with that function. Okay, this black curve here, this is the power. So what do you see here? Again, the power is negative when V and I have opposite signs. So look at this one here. I is negative, V is positive, and the power is negative. Here, here current is positive, voltage is negative, then power is negative. But the power is positive when they have same signs, like this one, current here positive, voltage is in the positive side, then the power is also positive. And here we have, for example, current is negative, voltage is also negative, then the power is positive. What about the average power? Since this power oscillates around the horizontal axis as a function of time, the average power is also 0 for the capacitor in an AC circuit. Okay, do you have any question here in that part? Then let me continue with the power in a general AC circuit. Here we have discussed a pure capacitor in an AC circuit, pure inductor, and here we have pure resistor. So what about an LRC circuit? We have resistor, inductor, and capacitor in a circuit. So what is the power here in that circuit? So again, the current in that circuit is given by that expression, I times cosine omega t. Current changes as a function of time. And then we have calculated voltage within that circuit. We have done it during the last lecture. This is given by V times cosine omega t plus phi. So what is the phi? Phase angle between current and voltage across the AC circuit. Okay. So we have discussed all these things. This is the voltage in the inductor. This is voltage across the capacitor, and this is voltage across the resistor. Then with the vector sum of all of them, we have voltage across that AC circuit. Okay, so this is the current phasor, this is the voltage phasor, which is given by I times Z impedance of the AC circuit, and here we have phi angle, phase angle in between. Okay, you see here. So what about the power? So power of that circuit can be written V times I. V is this one, put it there. I is this one, put it there. So this will give us that black curve here. What do you see here? The power is oscillating as a function of time, you see. So some part of it in the positive side of the horizontal axis, but some part of it is also located in the negative side of the horizontal axis. But if you look at the average power, it is always in the positive side. So in case of pure capacitor, we have zero average power because power is oscillating around the horizontal axis, symmetric. And in case of inductor, again, average power is zero. Here we have always positive power, okay, due to the cosine square omega t. within that power equation. So, but in case of a general AC circuit, we have power like this. Again, the average power is positive. And average power is given by 1/2 V times I cosine phi. Phi is the phase angle here. So now I will show you how to calculate this average power. Power is given with that expression, and have to calculate average power in a general AC circuit. So here we have cosine omega t plus phi. You can consider like this, cosine A plus B, okay? So use the relation from the trigonometry for the cosine A plus B. So you can write it like this, cosine A times cosine B minus sinus A times sinus B. You remember from the trigonometry, right? So just open this one, V times cosine omega t cosine phi minus sinus omega t sinus phi. Then here we have I cosine omega t. Okay, so if you multiply this term with that one and multiply this term with that one, finally we will have that expression for the power. Vi cosine phi cosine square omega t minus Vi sinus phi cosine omega t sinus omega t. So what about the average value of cosine square omega t? We have already discussed this one in the previous lecture. The average value of this function is 1/2. Okay, cosine square omega t like this. This one. Okay, here remember the power in a resistor. Put cosine omega t here and put cosine omega t here. You will have cosine square omega t. Power will be like this, and the average is given by 1/2. 1/2 comes from cosine square omega t. We have also done it in the previous lecture. So the average value of cosine square omega t over one cycle, like this, is 1/2. So put 1/2 here in order to calculate average power. And here we have cosine omega t times sinus omega t. I can write this function like this, 1/2 sinus 2 omega t, okay? This is a sinus function, and sinus function will oscillate like this around the horizontal axis. Then its average value over a cycle will be 0, okay? So we will have 0 here from the second term, and here we will have 1/2. So here we have Vi cosine phi. So the average power is given by 1/2 Vi times cosine phi. This is the average power of an AC circuit. Here we have Vi half. Remember that one. Vi half, instead of Vi half, I can write this expression and this expression. So it will give us Vrms times Irms. Just do the same here. Instead of Vi half, just write Vrms, Irms, and cosine phi here. Okay, is it clear? Do you have any question here? Okay, then let me continue. If V and I are in phase, like in resistors, remember the pure resistor, this is the current phasor, this is the voltage phasor, and the phi angle in between is 0, okay? They are in phase. Then the average power, just put 0 here, cosine 0 is 1, then the average power is written with 1/2 Vi or Vrms Irms. Look at the result. If the phi angle is 0, or phase angle is 0, the result goes to the power in a resistor. You see, because cosine phi is 1, this is the maximum value of the power in an AC circuit. If the phase angle between V and I is 90 degrees, so remember that one, if you have phase angle phi, which is equal to 90 degrees, then the average power is 0. Just put 90 degrees here, cosine 90 is 0, okay? Then the average power is 0. So this happens in inductors and also in capacitors. So remember the phase diagram for the inductor. What we have here, phase angle is given by 90 degrees. Then the average power is 0. You see, we have already done it. And here we have we have a capacitor, and we have phase angle between current phasor and voltage phasor, and this angle is 90 degrees. Then the average power, this is the power, instantaneous power, and this is the average power. Average power is 0. So you can also understand this one, that there is a 90 degrees here between V and I. Just put 90 degrees, then average power is also 0. So in general case, we have angle phi between V and I like this. This is the voltage of the AC circuit. This is the current in the AC circuit, and this is phi angle in between. So, and then average power is written with that cosine phi function. And here we have another important information. For the LRC series circuit, we have voltage of the circuit like this, given by I times Z, and this is the current. And here we have a phi angle in between. You see, this is VR, voltage across the resistor. So if you write V times cosine phi, this will give us VR, right? Maybe you better understand with that figure. So here we have V, voltage across the LRC series circuit. And here we have phi angle between voltage phasor and current phasor. Then this component along the current phasor is given with V times cosine phi. So look at that one. V times cosine phi is equal to voltage amplitude across the resistor, right? So we can understand that the average power dissipated in the resistor in LRC series circuits. Here we have an LRC circuit, and the power is delivered to the circuit with that source, and that power is dissipated here, not in that one, not in that one, because the average power of the capacitor and the average power of the inductor is 0. So power is dissipated within the resistor. Okay, don't forget this one. So now let me talk about the power factor. This cosine phi here, cosine phi, is called the power factor of the circuit. And if you have pure resistor, the power factor is 1. If we have pure resistor like this, phi angle is 0 because current and voltage phasors are in phase, okay? So phi is 0, then cosine phi is 1. So power factor for pure resistor is 1. And usually in devices, in real devices, a low power factor is undesirable in power circuits. So what is the meaning of low power factor? Cosine phi is the lower factor. Low power factor means that if you have 0 degrees, then we have 1, the maximum of the cosine function, right? If you have larger angles between current and voltage phasors, then this cosine phi will decrease, right? Then we will have lower power factor. So this is undesirable in power circuits. Because, look at this one. If this is smaller, in order to get some certain power, you have to derive more current, okay? But if this is bigger, then you need less current. If you have large currents in a circuit, then we will have large I square R losses in the transmission lines. So many types of AC machinery drove a lagging current. What is the meaning of lagging current? Like this, voltage leads the current phasor, then phi is bigger than 0, okay, and cosine phi is lower than 1. So what was the intended power factor? The intended power factor is 1. This is the best value for us. So in order to reach 1 here, we can use a correction, and we can do that correction by using capacitor in parallel with the load. So if you connect a capacitor here, but you must connect it in parallel, okay, then you can correct that power factor to the 1. Of course, the capacitance of the capacitor is important. Do you have any question here in that part? Okay, then let me continue with the power in a hair dryer. So an electric hair dryer is rated at 1500 watts. This is the average power at 120 volt, the RMS voltage. This is the voltage in the United States and Canada we have discussed before. In Turkey, the RMS voltage is around 220 volt. So calculate the resistance, calculate the RMS current, and calculate the maximum instantaneous power. Assume that the dryer is a pure resistor. There is no capacitor, there is no inductor within the hair dryer. So, first question, what is the resistance? Resistance is given by V RMS square over P average power. We have done it in the previous transparencies. Average power in a resistor is given by I square R, or V RMS square over R, or V RMS times I RMS. Okay, we have done it just in previous transparencies. So here we have V, which is given, and we have P average, which is also given. Then you can calculate the resistance of the hair dryer. And the second question is, what is the RMS current? So by using that expression again, okay, average power is given by V RMS times I RMS. I RMS is asked, then take this I RMS from that expression, P average over V RMS. P average is given, V RMS is given, then the RMS current is given by 12.5 amp. And the last question, maximum instantaneous power. The instantaneous power in a resistor, pure resistor, in a circuit, in an AC circuit, which is given by VI times cosine square omega t. So here we have VI. VI is the maximum instantaneous current. Look at this one. This is the P as a function of time. P is changing like this with that function, okay? in a pure resistor in an AC circuit. So what about the maximum value of that instantaneous power? The maximum value is V times I, okay? V times I, which is S. Then this is equal to 2 times average power. This is the average power. And this maximum is 2 times higher than the average power. You see, average power is given. Then we have maximum instantaneous power given by 3000 watt. Do you have any question here? Then let me continue with the power in an LRC series circuit. So in the previous lecture, we have solved an example, and within that example, we have calculated voltage and current in an LRC series circuit. So here, with the same question, it asks that calculate the power factor. Power factor is cosine phi, okay? And in the previous lecture, we have calculated phi 53 degrees for that example, okay? Just put 53 degrees in cosine function, then we have 0.6 power factor. And what is the second question? Calculate the average power delivered to the entire circuit and to each circuit element. This is the average power, and cosine phi is known, and V and I from that example, just put them, and the average power is 1.5 watt. And all of this power, 1.5 watt, is dissipated in the resistor, okay? So the average power delivered to the inductor and the average power delivered to the capacitor are always zero, okay? We have already discussed this one. So all the power delivered to that circuit is dissipated within only the resistor. Do you have any question? Then let me continue with the resonance in AC circuits. So you can better understand that resonance if you understand the working principle of the radio receiver, okay? So this is all type radio, and here there is a transmitter or radio station, okay? And it transmits radio waves with certain frequency. Remember the omega, okay? Omega angular frequency. So you produce some certain signals here, radio waves, radio frequencies, and then you transmit them. So there is an antenna here. So within the radio, there is also another antenna, okay? So then you can receive that radio waves, and then you can listen that radio station, okay? This is the working principle. So what we have within that transmitter in radio station and what we have within the radio receiver, both in transmitter and also in the receiver, we have LRC circuits, okay? Here we produce an alternating current with some certain omega frequency. And then here we have an antenna, okay? Radio waves are transmitted. And here we have another antenna in the receiver, antenna of the radio you can consider, okay? And here we have an LRC circuit. So the source is AC. Radio waves are coming with AC omega frequency, and then this AC source produces a current in that circuit. Okay, this is the working principle of the radio receiver. So let's go into detail. A radio signal of any given frequency produces a current of the same frequency in the receiver circuit here. Okay, but the amplitude of the current here, amplitude of the current within that circuit is greatest if the signal frequency equals the particular frequency to which the receiver circuit is tuned. So you have to tune the angular frequency of that circuit to the angular frequency of the transmitter. Okay? If the angular frequency in that circuit, in the receiver, becomes equal to the angular frequency of the transmitter, then you can see the maximum current here. Okay? So, for example, within the transmitter, radio station emits signal with some certain megahertz, let's say, and you have to adjust your radio receiver to this certain megahertz which radio station transmits. Okay, so omega frequency here must be equal to the frequency of the radio station. Then you can tune it. If the angular frequency of the receiver within that circuit is equal to the angular frequency of the transmitter, then we will have the maximum current here. Okay, this is called as resonance. So what is the meaning of that? This circuit in the receiver gives maximum current, and for other frequencies, we see very low currents in the signal. So if you convert this idea to the radio receiver, it means that the other frequencies produces very low currents, and they cannot produce an audible sound come out of the radio speaker. So you can only hear some sound if you have tuned frequency of the receiver. So this is the working principle of the radio receivers, and the mechanism is called as resonance. So I will go into detail here. So this is the amplitude of voltage across an AC circuit, which is given by current amplitude times impedance of the circuit, which we have discussed during the last lecture. So what is the impedance? We have also calculated impedance of an LRC series circuit during the last lecture, which is given by square root of R square plus square of omega L. This is reactance of the inductor minus reactance of the capacitor. We have done it. So what we see here, reactance of the inductor and also reactance of the capacitor depends on the omega angular frequency. Okay, so if the reactance of the inductor and reactance of the capacitor are equal to each other, this term here will be 0. Okay, and the impedance of the circuit will be equal to the R, okay, with that expression. Then here we have impedance, and here we have voltage amplitude across the circuit, and here we have current in the amplitude. So now let's continue. Here we have omega in logarithmic scale, angular frequency, okay? And this is the R resistance, reactance, and also impedance. So what about the reactance of capacitor? Reactance of capacitor is given by that expression, 1 over omega C. If omega increases, this is decreasing, you see, because it is inversely proportional to the angular frequency. What about the reactance of the inductor? it is proportional to the, directly proportional to the omega. Then if omega increases, reactance of the inductor also increases in logarithmic scale like this. What about the impedance? Impedance is given by resistance and reactances of the inductor and capacitor with that expression, right? So if reactance of the inductor and reactance of the capacitor are equal to each other, this term is zero, and impedance becomes equal to the resistance. And resistance of the resistor in an AC circuit never changes by angular frequency. We have discussed this one during the last lecture. Resistance is independent of the omega, okay? It is constant, you see? This is logarithmic omega, and this is constant. Resistance is constant. And if they are equal to each other, this impedance is also equal to the resistance. And for increasing omega and for decreasing omega, impedance has that type of relation. Okay? So if XL, this reactance of the inductor and the reactance of the capacitor are equal to each other, then this term is zero. This condition happens for only special angular frequency, okay? At that frequency, which is also called resonance, the impedance Z has its smallest value, this one, smallest value here for certain angular frequency, which is equal to the resistance of the resistor. And what about the relation between impedance and current? We have constant amplitude of voltage across an AC circuit, and you decrease the impedance, you increase the impedance. So what happens to the current? I can show you that relation in that graph. This is again logarithmic scale, logarithmic angular frequency. And here we have current and impedance with that relation. So for certain omega frequency, this term is equal to this one, and this is zero, okay? And impedance reaches to its smallest value here. Then for the smallest value of the impedance, we have maximum value of the current, you see? So current is decreasing if you're far from the resonance frequency, and again here current is decreasing if you're far from the resonance frequency. And this is the impedance as a function of the logarithmic angular frequency. And so again, I'm repeating that this resonance occurs if that reactance of the inductor is equal to the reactance of the capacitor. And this only happens if the omega is equal to the resonance. So if the omega is equal to omega 0 for the resonance condition, and this resonance frequency can be calculated like this. What we have said that this XL is equal to XC. XL is given by omega 0 times L. XC is given by 1 over omega times C, 1 over omega 0 times C for certain frequency. Then from that expression, take omega 0, then we have resonance angular frequency, which is given by 1 over square root of LC. This is inductance of the inductor here, and this is the capacitance. Do you have any question here? So now let's discuss how to tune the current within that circuit. How to manipulate the current here. In an LRC circuit, we have resistance, inductor, and capacitor. So how to tune the current here? So let's consider that this is constant, okay? We have AC voltage here, and we would like to manipulate the current in the circuit. In order to manipulate the current here, you can manipulate the impedance. So how to manipulate the impedance? You can change the resistance of the resistor, or you can manipulate the reactance of the inductor here, or you can manipulate the reactance of the capacitor. So if you play with one of them or with all of them, then you can manipulate impedance of the circuit. Then you can manipulate the current in the circuit, right? So how to manipulate with impedance? You can replace this resistance with bigger ones or lower ones, then you can manipulate the impedance and current. So just keep resistance is fixed. You can use a ferromagnetic core within the inductor coil. Then you can also manipulate the inductor, manipulate the reactance of the inductor with moving the ferromagnetic core into the coil or out of the coil. So this is another choice to manipulate the impedance and current in the circuit. Or you can produce plates, but one of the plates of the capacitor is movable. So if you manipulate the capacitance, then you can manipulate that term, reactance of the capacitor. Then you can also manipulate impedance of the circuit. So then you can manipulate the current in the circuit. So this is how to tune current in LRC series circuits. So in all type of radio receivers, capacitance of the circuit is manipulated, and also in some of them, reactance of the inductor is manipulated. Then you can manipulate the current within the circuit. Okay, so here I will show you current in the circuit as a function of 3 different resistance. So first of all, I have huge resistance of resistor, and as a function of the angular frequency, I have that current. So here I see the maximum current for the resonance frequency, okay, omega 0 here. But what do you see here? The resistance of the LRC series circuit is huge here. If R is bigger, then this impedance is bigger. If the impedance is bigger, then the current is lower, right? If I decrease the resistance from 2000 ohm to the 500 ohm, then I can also decrease the impedance. If I decrease the impedance, current will be increased. You see, current is increased. If I further decrease the resistance, I can further decrease the impedance, then I can further increase the current. Then I have current like this for lower resistance in LRC circuit. So with that one, you can manipulate the current in the LRC series circuits. Do you have any question here? Okay, then let me continue with example from the book 31.8, Tuning a Radio Receiver. So the series circuit here, this one, what we have here, we have an AC source, and here we have a resistance, here we have an inductor, here we have a capacitor, LRC circuit, okay? is similar to some radio tuning circuits. It is connected to a variable frequency AC source, this one, with an RMS terminal voltage of 1 volt. Find the resonance frequency. Resonance frequency is asked, and find the inductive, at the resonance frequency, find the inductive reactance, find the capacitive reactance, find the impedance, and find the RMS current, and find the RMS voltage across each circuit element. So what is the RMS voltage across the capacitor? What is the RMS voltage across the inductor? What is the RMS voltage across the resistor? So start with the first one. Find the resonance frequency. Resonance frequency is given by 1 over square root of LC. L is given 0.4 millihenry. Put it there. Capacitance is given by 100 picofarad. Put it there. Then angular frequency can be found in radian per second. Okay, you can convert this one to the frequency. Okay, so which is given by 2 pi f, right? So then you can calculate 800 kilohertz. This is the frequency. This frequency is in the lower part of the AM radio band. So now B, at that resonance frequency, find the inductive reactance, find the capacitive reactance, and find the impedance. Inductive reactance is given by omega times L. Omega is calculated here, put it there. L is given, put it there. Then we have ohm, the result. And again, put omega here, put the capacitance here, then you can calculate the capacitive reactance and find the impedance at the resonance frequency. We have already discussed that at the resonance frequency, XL is equal to XC, right? Then impedance is equal to the resistance. Then resistance is already given, then impedance is equal to resistance. So what is C? What is the RMS current? RMS current can be calculated by using that expression. VRMS is equal to IRMS times impedance. Impedance is given by R, put it there, 500 ohm. And VRMS is given 1 volt, this one, voltage across the circuit. Put it there. Finally, we have RMS current, 2 milliamp. We have 2 milliamp current within that circuit. And what about the RMS potential difference across the resistor, inductor, and capacitor? For the resistor, the voltage or potential difference can be written like this. RMS current is known, put it there. R is known, put it there. 1 volt here we have. So what about the RMS potential differences across the inductor and capacitance? You can calculate like this: I times reactance, I times reactance. Current is known, we have calculated, put it there, put it there. And we have also calculated reactance of the inductor, reactance of the capacitor, put them here. So here we have 4 volt here. So what do you see here? The voltage across the resistor at the resonance frequency is equal to the voltage across the circuit. Okay. Do you have any question here in that point? Okay, then let me continue with the last part of my lecture. This is very useful in industry and also for daily life applications at home. So listen carefully. This part is very easy to understand. I have shown you that picture in my previous lecture on Tuesday. I will repeat it today. So this is electrical power distribution system in general, okay? So we use transformers, every part of that system. I will go into detail. So this is the power plant. You produce electricity here. And in order to carry the electricity from power plant to the home, you have to increase the output voltage by using step-up stations, okay? So you increase the voltage, you step up the voltage to the kilovolt range. So then it is cheaper, it is easier to distribute the electrical power, okay, at very high voltages. So in order to use that electricity, that electrical power at home, you have to step down the voltage, okay? So these are the high voltage transmission towers, and these are used in the city center, let's say. So you step down the voltage here, and then in order to use the electricity at home, you have to further step down the voltage, okay, to the 240 volt, for example, for Turkey, okay? Here we have kilovolt range. You cannot use it at home. So you have to decrease the voltage. So in order to step up the voltage, in order to step down the voltage, in order to step down the voltage, we have to use transformers, okay? So today we will see the working principle of transformers. In addition to that, during the last lecture, we have discussed AC adapters. For example, this is an AC adapter for laptop, okay? So you get AC current, and then there is a transformer here. Then here, for example, you get 240 volt AC from the wall socket at home, and you decrease that AC voltage to the lower values, step down transformer we have here, okay? Then this AC voltage is also converted to the DC, okay? By using rectifier. We have discussed the details, but we don't have any job today with that region. We will only deal with the transformer. Transformer step up or step down the AC voltage to the AC voltage, okay? But in order to convert the AC voltage to the DC voltage, then you have to use diodes we have discussed during the last lecture. But today, we will mainly concentrate on the transformer. So what is transformer and how it looks like? So this is the iron core, ferromagnetic material. And we have a coil here on the left side. This is primary winding. And we have also another coil on the right side. This is called a secondary winding. And here we have source of alternating current. Okay, source of alternating current. And here on the right side, you have a resistor. Okay. So if there is an alternating current here, what do you expect? This alternating current will produce a changing flux, right? Changing flux here. So if you have a changing flux here, via this iron core, you will also have a changing flux here. If you have a changing flux here, then you will have an EMF and also an alternating current within that circuit. This is mutual inductance we have done in the previous chapter, right? So first of all, we have alternating current here because AC voltage is supplied by the wall socket. Then here we have alternating current, okay? And due to the alternating current here within that coil, we have a flux change. Flux changes by time, okay? And then due to change in the flux, here we also have same change of the flux within the second coil, okay? Then here we also have an alternating current due to the EMF, okay, within the secondary winding. So this change in the flux of the coil, first coil, gives us EMF in the primary winding or the first coil, then which is given by minus N1 times change in the flux, magnetic flux. N1 is number of turns, okay, in the coil. And due to the changing flux, we also have EMF here, and this second EMF is given by minus N2 times change of the flux as a function of time here. So N2 is the number of the coils here in the secondary winding. Look at that one. This change in the flux in the primary coil is equal to the change of the flux in the secondary coil. So with the help of the iron ferromagnetic core here. So then if these are equal to each other, then I can get that expression. EMF2 over EMF1 is equal to N2 over N1. Number of the coils in the secondary winding and number of the coils in the primary coil. And we will have potential difference here. We will also have potential difference here across that resistor connected to the secondary winding. Then I can get that expression. V2 over V1 is equal to N2 over N1. Okay, this is the working principle of a transformer. So if you supply a power to the primary coil, then the secondary coil delivers power to a resistor here. So now let me continue. Here we have number of turns in the secondary coil. If the number of turns in the secondary coil is bigger than the number of turns in the primary coil, like this one, we have more turns here compared to this one, then V2 is bigger than V1, and we have step-up transformer. So I can consider like this. Here we have 12 kilovolt, and then here we have 400 kilovolt. You increase the voltage, okay? This is step-up transformer. If N2, number of turns here, is lower than the number of turns in the primary coil, then V2 is lower than the V1, and we have a step-down transformer. For example, here you have to use step-down transformer for the AC adapters for household devices. And also here for the step-down substation, and also step-down drum transformer here, you have to use step-down transformers, okay? So now let me show you one bio application. Actually, it is not application, but it is just related to the bio, okay? Related to the health of the people. Dangers of AC versus DC voltages. Which one is dangerous? AC voltage is dangerous or DC voltage is dangerous? So alternating current at high voltage above 500 volt is more dangerous than direct current at the same voltage. So AC is more dangerous. Why? When a person touches a high voltage DC source, it usually causes a single muscle contraction. Muscle contraction is this one, okay? Kas kasılması, but single time. So so it is single, okay? Just your muscle is contracted. So it usually causes a single muscle contraction that can be strong enough to push the person away from the source. Okay, it is like this, just single muscle contraction. But in case of AC, touching a high voltage AC source can cause a continuing muscle contraction like this. Okay, because you have AC current. So you cannot get out of that AC source, then it is very dangerous. For the DC one, just single muscle contraction. Okay, it pushes you away from the source. But in case of AC, it prevents the victim from letting go of the source. So you stay at the source and you are behaving like this, many muscle contractions. So for this reason, the voltage here is lowered to that values to save the people at home, okay? You would like to recharge your mobile phone, and what to do? How many transformers we have to use to recharge the mobile phone or to use the electricity at home? So here, electricity is produced, and then by using step-up substation transformers, we used one transformer to step up the voltage, to transfer the electricity, okay, with less power losses. And here, in order to step down the voltage, we use again transformers, okay? And here we have again another step down transformer, okay? So now you have electricity with 240 volt AC at home, but it is still not enough for some devices. For example, for this one, 240 volt is too much, okay? In order to charge this one, you need 5 volts, but it must be DC. So here we have another transformer, step down the voltage, and we also have rectifier to provide DC current. Okay, so we use transformer here, transformer here, transformer here, and transformer here. Many transformers to the home appliance. Do you have any question here? I think you can understand the importance of transformers for our life. In Turkish, it is also called as trafo, okay? So what about the energy in transformers? Here, when we have an alternating current within the primary coil, we will have an EMF in the secondary coil, right? And this will produce a voltage across the resistor, and this will also produce an alternating current in the secondary coil. So then I can write the power for that coil, and also I can write power for that circuit, okay? But it is important to keep in your mind that the power delivered to the primary coil is equal to the power in the secondary coil. Don't forget this one. So then I can write that relation. V1 times I1 here is equal to V2 times I2, okay? So this is the power relation in the transformer. But what about the energy losses in the transformers? There are always some energy losses in the transformers. There are main 3 reasons for that energy losses. One is the windings have some resistance. So here we have a wire in the coil, okay? So this coil, this wire has some certain resistance. So due to that resistance, we have I square R losses. This is the one reason for the power energy loss or power loss. And here we have ferromagnetic iron core. We have discussed ferromagnetic materials. They have hysteresis curves like this, okay? And we have hysteresis losses. I will not go into detail. We have discussed this one in chapter 28. You can check your lecture notes. Okay, so we have hysteresis loss of the iron core. This is second reason for the energy losses in the transformers. And the last important energy loss in the transformer is eddy currents. Do you remember the eddy currents we have discussed in chapter 29? Okay, eddy currents also cause energy loss in transformers. So how? So remember the eddy currents. If you apply a magnetic flux changing by time, you produce eddy currents in metals like this, okay? They are used in metal detectors. We have discussed details in chapter 29. So I will not go into detail today. In order to decrease the energy losses due to the eddy currents, we use a laminated shape of the iron core here. This is a solid core, okay? And this is a laminated core. Then you can decrease the eddy currents. So how to do that? Let me show you. Normally, here we have one coil, let's say primary coil, secondary coil here, or primary coil, secondary coil. There are different designs of the transformers. And here we have ferromagnetic core. Here we have ferromagnetic core, okay? So, but this core is not a solid core. It is not single part. Here you see we have many plates. Can you see? We have many plates here. So this type of design is chosen to decrease the eddy currents and then to decrease the energy loss due to the eddy currents. So we have discussed three reasons for the energy losses in the transformers, and in order to decrease that energy losses, we can use soft iron cores. So they have hysteresis curve with smaller coercive fields, okay? And we can use lamination. I mean, you can use ferromagnetic plates in the iron core of the transformer. Then we can reach the efficiencies up to 90% or 99%, depending on the design. Okay, so here we have very nice example for the transformer. A friend returns to United States from Europe. You can consider that another type of journey. One of your friends went to United States and bought a coffee machine, okay? And you would like to use it in Turkey. Within that example, a friend returns to United States from Europe with a 960 watt coffee maker designed to operate from a 240 volt line AC, okay? This is the AC voltage source in Europe, also in Turkey, okay? And one lady bought that machine from Europe and she went to United States. But in the United States, the wall socket provides 120 volt, okay? In the United States and also in Canada, they use different RMS voltage at home. So the question is that, what can she do to operate it at the United States standard 120 volt? This machine is designed to work with that voltage. But in the United States, they have this one. So what to do to operate that machine? This is the first question. The second question, what current will the coffee maker draw from the 120 volt line in United States? And the last question, what is the resistance of the coffee maker? So the voltages are RMS values. So first question, what can she do to operate it at the United States standard 120 volt? So this machine requires 240 volt, but United States standard is 120 volt. So you have to step up the voltage, right? In order to step up the voltage, you need a transformer. Okay, you need a transformer. So what to do? Just look at this one. This is V1 in the United States, 120 volt. And this machine needs V2, 240 volt. And you have to design a transformer with that number of turns in the secondary coil and with that number of turns in the primary coil. So this primary coil will get the energy from the wall socket in the United States, and then the secondary coil will provide energy to the coffee machine, okay, or coffee maker. So put the V2 here, put the V1 here, then N2 over N1 will be calculated as 2. It means that the secondary coil connected to the coffee maker should have twice as many turns as the primary coil connected to the 120 volt line. What is the second question? What current will the coffee maker draw from the 120 volt line? In order to calculate the current, we can use this expression. So P average is given by V1 times I1. So P is given, okay, V1 is given, then I can calculate current, 8 amp. And what about the current in the secondary coil, okay? I can calculate it again by using the same expression. P is same, and V is 240 volt, then current is 4 amp. So what do you see here? Same coffee machine, same coffee maker. In United States, you have to use 8 amp, okay? And in Turkey and in Europe, you have to use 4 amp, okay? You have to drive a 4 amp in the circuit. So this use of 240 volt in Europe and Turkey, and also this use of 120 volt in United States or in Canada, both of them have some advantages and disadvantages, okay? I will not go into detail. So if you look at from the economic point of view, this is better, okay? So you need less current and it is also easy to carry the voltages at that values, okay? It is more economic, but this one is less dangerous for the people. So this has advantages, this has some certain advantages, but for high power machines, this is not useful, okay? For this reason, in the United States, usually in the new buildings, they also provide that type of sources for the appliance with higher powers. So what was the last question? What is the resistance of the coffee maker? Resistance of the coffee maker can be calculated by using that expression. V2 is equal to I2 times R. So then V2 is 240 volt and current is 4 amp. We have calculated in the secondary coil. Then the resistance of the machine is 60 ohm. So this was the last example of this chapter. And with that one, I have finished alternating current. And next week, on Tuesday, I will start with the electromagnetic waves. And next week, I would like to finish also the forthcoming chapter. And then we will finish that semester. Do you have any question? Any question? Then I will close the session. Take care of yourself. Bye-bye.